Greetings again, pre-calc students. This could be our last video, if I'm able to get this working, last video of the entire course. So it's been fun to go through all this with you guys. Hopefully you've benefited from this and learned. And here we go. This is the second half of the fourth lesson, rates of change in tangent lines. So we're going to pick up where we left off the other day. So we have a particular function here, y equals x squared minus 4x at x equals 1. We'd like to try to find the slope of the curve at that position. So again, let's see if we can review how to do that. Remember, we had our big limit expression. So it's the limit as h approaches 0 of the f of x plus h minus the f of x, all of that over h. And we did a couple problems related to that. So let's see if we could do that in this case. So again, the algebra here is a bit tricky. In this case, it's going to be then the limit as h approaches 0. Now I have to put this, remember, x plus h in place of each of the x's here. So not only in place of just this one, but also in this one. So this will be a little tedious, but it's going to be x plus h squared minus 4 times, well, I have another x, so I have to put the x plus h in there, like that. That's the first part. And then minus the f of x part. So now I can put the actual function in there. I'm going to put it in brackets like this, which is x squared minus 4x. For the sake of time, I should put the denominator in this h here, but I think I'm just going to add that in there at the end so I don't take up too much room. Alright, let's actually square this. So if I square, I'm going to get x squared plus 2xh plus h squared. Now I distribute the next part, minus 4x minus 4h, and then looking at my other part, it's going to be minus x squared plus 4x. Now if I did this correctly, I'll probably get some things that can kind of cancel out here. So sure enough, here's an x squared and a minus x squared. Here's a minus 4x and a plus 4x. And so those things cancel out. That helps me out quite a bit. So then what I have left here then, it looks like, is 2xh plus h squared minus 4h. Again, that h is in the denominator. Looks like I could factor out an h from all these. So I have 2x plus h minus 4, right? And remember, I still have that h in the denominator here. So those are going to be able to cancel out, I believe. So we'll cancel out those h's. And so now what I have left is the limit as h approaches 0 of 2x plus h minus 4. And again, as long as this h is approaching 0, basically I'm going to call this 0. Won't ever quite actually get there, but close enough. So my final answer then in this case is 2x minus 4. That's my slope. So that's the general form for that slope. I can then substitute whatever value I need to. So for instance, at x equals 1, I could put then just a 1 in place of that. I'd get 2 minus 4, which is negative 2. And that does kind of make sense. If I look at 1, it looks like the slope indeed at 1 will be negative. So that definitely fits the bill. Alright, so my answer there is 2x minus 4. That's the slope at that particular point. Let's then look at the next slide. And I just want to remember that 2x minus 4 before I forget here, so I'm going to jot that down. Okay, now the next slide is, except now we want to think about the equation of the tangent line at x equals 1. Now we remember that the equation of the slope was y equals 2x minus 4. And if we think about that, is that going to be the equation of the tangent line at that particular spot? Well, not quite. Remember what this tells us, what I found here, that's just a representation for the slope at that point. So we can say then at x equals 1, putting 1 in place of there as we mentioned before, 2 times 1 minus 4, I'm going to get negative 2. That is actually equal to the slope at that point. But I want an equation of the tangent line. So here's an equation, y equals mx plus b. That's the slope-intercept form of a line. I just found now that my slope is going to be negative 2. When x is 1, that's kind of the key thing here. When x is 1, that means I can put 1 in place of x. And maybe I could go back to my original function here and see what the y value should be there. So if I put a 1 in here for x, I'd get 1 minus 4, which is negative 3. Alright? And so there's my equation, substituting a specific value in for x and a specific value in for y. So I get negative 3 equals negative 2 plus b. b, remember, is my y-intercept, so if I add 2 to each side, I get that. And so now that I know what b is, and I know that what m is, I should be able to write my equation. And sure enough, it looks like it's going to be y equals negative 2x minus 1. And if we plotted that on here, I didn't graph that, but it looks like that should be about right. Y-intercept of negative 1 and a slope of negative 2. It looks like indeed that line would hit the point that we're looking for, and so that's the equation of the tangent line. Y equals negative 2x minus 1. Now the next slide, as you might guess, we're the normal line. And so if tangent just grazes the graph at that point, the normal line, a good way to think about that is the perpendicularity. So the normal line will always be perpendicular to the tangent line at that particular point. So really we can do a lot of the same types of things. Let's see what purple looks like here. Y equals mx plus b. Now the slope, perpendicular slope, we knew that the other slope at 1 that the tangent line was negative 2. So the slope we want here now is positive 1/2. Remember, the relationship on slopes between perpendicular lines is that opposite reciprocal idea. Again, I'm going to put in the coordinates of the particular point here, which was 1, negative 3, I think, right? And again, I'm going to try to solve this for b. So in this case, I get 1/2 plus b. I'm going to subtract 1/2 from each side. So b is going to be negative 3 1/2, or negative 7/2. So if I write my equation to the normal line, then it's going to be y equals 1/2 x minus 7/2. The normal line being perpendicular to that tangent line that we had calculated initially. Again, these are famous, very traditional problems of calculus that we've just done here today, and hopefully they will make some good sense to you. Right here, and this is an application now of some of the slope rate of change stuff that we have talked about. So equation for the free fall at the surface of Jupiter, give you an equation here, s equals 11.44 t squared with t in seconds. Assume a rock is dropped from the top of a 500-meter cliff. Find the speed of that rock at 2 seconds. Again, the 500-meter cliff, that's a little bit irrelevant. We're mainly going to look at this equation right here. Now, when you hear the word speed, that assumes a rate of change. because speed could be considered miles per hour, meters per second, that type of thing. And so that's really what we're looking at in this case, a meters per second type idea. So the idea is, could we first of all find the slope at 2 seconds of this particular function right here? So let's give that a shot. So again, we have to do our little limit expression here. And so it's going to be, as h approaches 0, of course, so we have the 11.44, and I guess we'll use, in this case, t plus h squared minus 11.44 t squared. And of course all this would be over h. I'm going to not write that every time here. So I'm going to have 11.44 times t squared plus 2th plus h squared minus 11.44 t squared. I'm going to distribute 2 times 11.44 looks like it'd be about 22.88 th. 11.44 h squared minus 11.44 t squared. As you might have guessed, some stuff cancels out here. The 11.44, negative 11.44. And so looking what we have left here then, as far as, remember we still have that h in the denominator, looks like I can factor out that h once again, one of the h's. So I have h and 22.88 t plus h, all of that over h. Again, we can do a little canceling here, like that. So my expression is this. Remember, this is still as h approaches 0. So it looks like my speed that I get here is going to be, I'll just write this out a little bit more formally. The limit as h approaches 0 of this whole contraption should be 22.88 t plus h. Since h is going to 0, we're going to kind of ignore that or treat it as 0. And I get 22.88 t. And so if I, at 2 seconds is what the problem says. So all I have to do then is put 2 in place of that. And so 22.88 times 2 should be 45.76, and it looks like this would be like meters per second. All right, thanks for hanging in there through all this messy algebra stuff. We'll work on this more in class tomorrow, and bye now.